this video that's all about logarithms and their derivatives. This is actually just going to be a portion of our notes for section 4.3 because the second part involves a topic called logarithmic differentiation. So before we get to all the mini examples that are coming up, I want to sort of provide for you guys at the outset here a summary of the key parts of this material on logarithms, and that is really one excuse me, there's one extra rule, which is that the derivative of a log base a of x, this derivative looks like 1 over the natural log of a times 1 over x. So, for example, when we apply this rule to our natural logarithm, and that is when a equals the natural base e, this rule becomes the derivative of the natural log of x is simply 1 over x. So probably there's at least a few of us who are feeling a bit confused already, or at least annoyed at this notation in reference of logs and ln's. And so thankfully we'll begin these notes before getting to these two main points with a quick review of what logarithms are and how to sort of think about them. So let me zoom in on this picture here, at the risk of making everything too big. There it is. So in blue here, we have a function, an exponential function, y equals a to the x. And in red, we have the line y equals x. So one thing to note, right, is these exponential functions all pass through this point when x is 0, a to the 0 equals 1. And as we discussed right before our long spring break, to get a graph of an inverse function, you can reflect your original graph through the line y equals x. And so when we reflect through the line y equals x, this single point 0, 1 gets reflected to the point 1, 0. Excuse me. There's a couple other points I can single out on this graph. For example, excuse me, this point here, this would be the point when x is 1, and so on my exponential graph, that'll be a to the 1, that'll be 1, a. And when I reflect that across the line y equals x, and I'm able to do that by flipping the x's and y's, I'll get this point, and this point is a, 1. So if you were to take all the points on this blue exponential graph and reflect them into green points by flipping the x's and y's, you would get this green flipped exponential graph. And it turns out we don't have a good name for this until we decide to give it a name. We call this the inverse of a to the x, we call it the logarithm base a of x. So that's this inverse. And so what does it mean? Excuse me. What does it mean to say that this graph, that this function is the inverse? Well, we can sort of review a little bit about what that should mean. For example, what we know is that when we compose these two, maybe I'll write this in red, when I do the log base a of a to the x, right, put one function inside the other, they completely cancel. This also happens if you compose it the other way. If I do a to the power of log base a of x, all these functions cancel and we're just left with x. Right, and you can see this in some of the points I've indicated below. Right, we had a to the 0 equals 1, and so the log base a of 1 equals 0. Right, that was where our x's and y's being flipped. As mentioned here in these notes, if you use a base of a equals 10, most mathematicians, or at least math textbooks, won't call it log base 10 of x, we'll just call it log of x. So that's actually something important to remember. Whenever you see log x with no base written, you're talking about the log base 10 of x. So this is the inverse of 10 to the x. Similarly, when a is our natural base, e, the inverse of e to the x is written ln. It's pronounced the natural log of x. And that's the way we'll write it. It means the inverse of e to the x. Okay, so just a couple of notes here. The natural log of 0 is undefined, and why is this true? Well, if one, you can see it from the graph. Look at the graph of the natural log of x, but really, you can think about it like this. Let's say the natural log of 0 were to equal something. Let's just give that a name. Let's call it y. Well, what would this mean? This would mean that 0 would equal e to the y. And this is impossible, because as we discussed in our last video, as part of our calculus examples, e to a number is always positive. It can't be 0. Okay, so just like the behavior of our exponential functions, a to the x, are different depending on the value of a, their inverses, the log base a of x, are similarly different. So here's just a sort of review picture. When a is bigger than 1, so for example they have the log base 10 down here in green, we have this function that's increasing and that has a vertical asymptote at x equals 0. But when a is smaller than 1, like in this red example, a equals 1/10, we have a function that's decreasing, but it also has a vertical asymptote at x equals 0. And again, we can sort of get these properties really for any number a. It doesn't have to be 10 or 1 over 10. And something else we can notice about these logarithmic functions is the following, which maybe I'll write in orange. The domain for the log base a of x is all positive numbers, not including 0. Okay, that's mentioned down here in these typed notes. And it also says, hey, look, the range of the outputs of the natural log of x, right? If I look at this red graph or this green graph, log base a of x, I can get any positive number and I can get any negative number, right? So one thing you'll note here is this is switched, right? The domain for the inverse function is negative infinity to infinity, and the range for the inverse, so for the exponential a to the x, is 0 to infinity. You always get a positive number. All right, and it's not an accident that the domain and range for one function get flipped when you compare it to its inverse. Okay, so that's sort of a quick crash course in reviewing logarithms. There's a few other properties we'll get to that make logarithms really, really useful. But like example 1, for example, just has a quick question about what it means to form this weird function, the natural log of the natural log of x. All right, and so let's make this a Popper question that maybe we can answer. So Popper question 1, what is the domain of this function? The domain is, and let's give us some answers, negative infinity to infinity, zero to infinity, negative infinity to 0, just 0. So just x equals 0. Okay, so it's probably good to pause the video and think about this here. But if you've given yourself an opportunity, let's try and think it through ourselves. Well, one thing we have to be a little careful about here is this is a composition of functions. And so this inside function, natural log of x, has as the domain x can be in the interval from 0 to infinity, right? We can take the natural log of any number that's bigger than 0. But here's the problem. Once we take x and plug it into this first natural log of x, we can get any number between negative infinity and infinity. Right? That was us, we just said that a second ago. The range of natural log of x can be any real number. Okay, so now when I want to take the natural log of this thing, of this natural log of x, I could be in trouble. Right? If the natural log of x happened to be 0 or negative, then I'm going to plug the number 0 or a negative number in here, and I'm not allowed to do that. So we need this inside natural log of x to be positive. And how on earth are we going to figure this out? Where is the natural log of x positive? Well, we can think about it visually. Right, the natural log of x is going to look something like this. And we think, okay, where is the natural log of x equal to 0? And we sort of reviewed that point. That's at the point 1, 0. So if x is bigger than 1, then the natural log of x is bigger than 0. So that's what we need. We need x bigger than 1. And if you look at my answer choices, I did not give you that answer choice. I promise not to do that very often for these poppers, but the correct answer choice is going to be E. X can be any number bigger than 1. Okay, so that example was sort of forcing us to think about the domain of a natural logarithm, or logarithms in general. These two properties were the ones I mentioned above, so these two are just saying that the function a to the x and the log base a of x are inverses. So, for example, log base 2 of 2 to the 3, this is the sort of problem we would have you guys look at in an algebra course towards the end of the semester. But this looks like a complicated mess, but if you think about it, this is really log base 2 applied to the function 2 to some input, and the input happens to be 3. Right, and as we mentioned before, log base 2 and 2 to the x completely cancel. So what you're left with is just 3. If you really want to think about it, it's kind of like saying, oh, those two things just cancel because they're inverses. Similarly down here, the natural log of e, well, think about it, natural log, if you want to, you could write as that's the log base e, and e I could write as e to the 1, so those will also cancel, and I'll get 1. Okay. How about e to the natural log of 5? Well, if you want to write this, just to remind yourself how it works, that's e, and you're plugging into the e function. It's inverse. The natural log is the log base e, the inverse. So these two pieces cancel. And once again, you're left with the number 5. Okay, so I'll let you practice this question here as a popper question 2. And this time I promise to give you an answer choice that's in here. What is 3 raised to the power log base 3 of x? Is it option A, x? Is it option B? I'll change colors. Is it option B, 3? Is it option C, E? Is it option D, 3 to the x? Okay. So here is, our notes call this a fact. Again, this fact isn't a new fact. They're saying, hey, this equation, y equals the log base a of x, is the same thing as writing this other equation. And that might feel like an unrelated fact, but all this is saying is, again, log base a is the inverse of a to a power. So a to a blank. But this can feel like a separate fact when you're using it. So this example down here is actually a pretty good one to maybe pick on. 2 to the 5th equals 32. We can go take out a scrap sheet of paper and multiply 2 against itself 5 times and see that that's correct. The point is, we can rewrite this equation using logarithms. Right? So the way I think about it, when I usually think about it as starting with an equation that has logarithms. So when I have log base a of x equals y, I write this as a to the y equals x. So that equation is the same thing as saying x equals a to the y. So if I try this with the second example down here that starts with a log equation, I'll have log base 4 of 16. Alright, that's supposed to equal 2. Well, that equation is saying that 4 squared equals 16, which is maybe an easier equation to verify is true. Okay, so these logarithm laws are really, really useful. In fact, historically speaking, this is why logarithms were invented. Logarithms have this lovely property. They tend to make math easier. Now, the cost of this, of course, is that logarithms are hard to think about, right? Like log base 2 of 7. I don't really know what that number is. But one of the benefits, even though logarithms can produce weird outputs, one of the benefits of logarithms is that they make mathematical operations easier. So for example, the product rule for logs says this: if you take the log of a multiplication of a product, it turns the multiplying, like magic, into the simpler operation of addition. So the log of a product equals the sum of logs. This was one of the main reasons logarithms were first invented and used way back before we had calculators, because multiplying numbers took a lot of time and effort, and if you use logarithms, it turns multiplying into adding. Similarly, if multiplying gets turned into adding, dividing, or taking a quotient, should get turned into subtracting. And the last rule is it says, okay, if you take the log of a power, it's going to convert that, taking x to a power, and it converts it into just multiplying by a constant. So we want you to feel comfortable using these. These are going to pop up, so they might seem weird to state as laws, but when you start practicing them, like we're about to do in example 2, they will start to feel like second nature. If you're curious, you might be wondering, why are these true? And I'll just sort of quickly summarize the answer here. The answer as to why these laws are true: these are the undone laws for exponents. Right? Exponents, right? Exponentiation, which is supposed to be the inverse of logs, has this complicating fact. If I take a to the x and I add y, if I add two exponents, so I'm doing a to a sum, that gets broken up into a product, a to the x times a to the y. And so one way to think about this is exponentiation turned this addition of inputs into multiplication of outputs. It turned addition to multiplication. Since a logarithm is the inverse of an exponential, it will undo this rule. Okay, that's where these come from, but let's start using these rules. So here's a really good example of one. Example 2. it says, let's simplify this expression, the natural log of this weird-looking fraction that has a bunch of variables in it. So, here's the way I think about it. I say, oh, look, I have the natural log of a fraction. Well, logarithms turned dividing into subtracting. So I take the natural log of the numerator, and then I can write that dividing sign as a minus, and then I have the natural log of the denominator. That already looks a lot nicer. But wait, there's more, because that first natural log term is a product. So I can break that up and saying, oh, the natural log of x cubed times y, well, that times I can write as a plus. That'll turn into the natural log of x cubed plus the natural log of y. Similarly, in that second product, in that second term, I have another product. So I'll have, that's the natural log of z, and then I'll have a plus the natural log of the square root of x plus 1. So we're making this expression longer. It takes more horizontal space to write, but the terms involved are looking a lot simpler. In fact, there's even more simplifying we can do. That natural log of x cubed, one of the rules we just quickly reviewed that you might start to feel familiar from algebra, is that power rule, right? The natural log of x times x times x of x to the third power, we can bring the 3 down out front and leave the x in there. And now I've got plus the natural log of y, and then I have minus the natural log of z, and then I have minus the natural log of the square root of x plus 1. And one thing that dealing with logarithms and when you want to deal with derivatives, it's really helpful to write our square roots as to the 1/2 power. So again, I have one more simplification I can make. That last term over there has a giant ugly fraction power, but I can pull that power down out front using the logarithmic power rule. And now I can leave my expression like this. So I think I kept using the word simplify here. Really what I was doing was expanding this expression. Arguably this isn't making it look simpler, except that each term now involves a simpler expression. Okay. Alright, so this example 3 wants us to simplify, by which they mean use the logarithm rules to write this as a logarithm of some nasty expression. So if that first term, let's see, maybe I can color code it, I'll write in red, that first term equals, that's 1/3 log of x, and that's supposed to be read as log base 10, remember? That's log of x to the 1/3 power. And this term here, there's not a whole lot I can do. It's got a minus sign in front of it. So maybe I'll just leave that one alone for right now. But the last term, which I guess I'll underline in blue, is minus 4 log z. And of course I can write that 4 as a power. So when I combine all these together, right, my expression is log of x to the 1/3 power minus log of x squared plus 1 minus log, okay, I'll put parentheses there, of z to the 4th. Okay, so if I combine these two expressions, well, I can say, hey, that's a difference of logarithms. That could have been somebody using our division rule. They could have said, oh, that was log of a dividing. And then I have one more subtraction of logarithms. So again, I could say, oh, that could have been coming from somebody who had done a log of this first term, this first fraction, divided by z to the 4th. Okay, so that's all of our review, and it is kind of a crazy crash course review. So feel free to take it slower with these concepts, but that's our review of some rules that help us manipulate logarithm expressions, and a review of what the logarithm is and exactly how it's related to exponential functions. But now we finally get to the calculus part of this, which is how do we take a derivative of these log functions? And the first one we think about is, well, how do I take a derivative of the natural log function? And if you like memorizing rules, here is a new rule to memorize. The derivative of the natural log function is 1 over x. They even say down here, in these sort of type notes, if u is a function of x, then we use the chain rule. So here's what they're really saying in these notes. If instead you are trying to take an x derivative of the natural log of u of x, well, then the chain rule is going to say, okay, I now have a rule for taking a derivative of natural log. That's my outside function. Its derivative is 1 over, and so I put my inside function. And now the chain rule comes in and I get u prime of x. So this will be u prime of x divided by u of x. Okay, so let's try that here in example 4. It says differentiate the following functions. So if I want to consider dy dx, or y prime, well, we're going to practice our new derivative rule. The derivative of natural log is 1 over. And now I just have to multiply by the derivative of that inside function. So when I take a derivative of that inside function, I'm going to get 12x squared minus 5, and that's all divided by 4x cubed minus 5x. All right, here's a good one. Maybe we'll make our third popper question this one. So let's make part B. This is popper question 3. What is dy dx for this example? Is it A, cosecant x? Is it B, oh, I don't know. What's a bad wrong answer I can make up here? cosine of x, is it c cotangent x, is it d, I don't know why I switched to blue, let me go back to red, is it d tangent x? So you should give yourself a moment to think about this, but really you should apply our rule for differentiating natural log and what we wrote in purple here, applying this rule when it's natural log of another function. Okay, so here's a bizarre function. In example C, it says, it doesn't even give us instructions, but I think what they wanted us to do is take f prime of x. And this is a kind of a bizarre function. It's a natural log of another function, 2x. So we can sort of think of this as like a triply composed function. It's like an onion of functions. We've got to differentiate each layer, starting with the outer layer, and then move to the next layer, and then finally to the innermost layer. So what's the derivative of this first natural log? That's our outermost function. That's 1 over. And what is it 1 over? It's 1 over whatever was plugged in to that first natural log. So it's 1 over the natural log of 2x times the derivative of all that stuff. Okay, so we're still not done taking a derivative, so now I still have that 1 over log of 2x. But now, what's the derivative of the natural log of 2x? Well, that should be 1 over 2x times the derivative of 2x. And if you want, as you should, we can simplify that derivative of 2x into exactly what you think it is. That's just the number 2. We can clean this up a little bit. We can cancel those 2's. So at the end of the day, we can rewrite our answer as 1 over x times the natural log of 2x. Okay, so example 5 gets us to taking a derivative to find a tangent line. And let's just check, whenever I see a problem like this, the first impulse I have is, let's make sure this point is actually a point on the graph of our function g of x. This is saying when x equals 1, g of x, g of 1, should equal this expression, natural log of 1/2. Let's just check that that's true. What is g of 1? Well, g of 1 is the natural log of 1 to the 4 over 3 times 1 squared minus 1. Okay, so this does indeed equal the natural log of 1/2. So let's just remember, it's been a while since we've talked calculus. Our equation for a line will be y minus y1 equals m times x minus x1. And we already know x1 is going to be the point 1, they told us that, and y1 is this weird number, the natural log of 1/2. So the only thing we really need to do this problem is the value of the slope, and that should be g prime at our point x, 1 equals 1. Okay, so finally we get to go back to differentiating some log stuff. And you'll notice, since g of x has this appearance, if we wanted to start differentiating this right away, right, what we would get is 1 over that fraction, and then times a derivative of that fraction, and we would use the quotient rule and get a bunch of stuff that we would need to carefully sort out. We could totally take a derivative that way, but if you want to avoid it, here, this funny natural logarithm function, because it has these nice properties, it allows us to rewrite this function in the following way. In fact, I can even rewrite it a little bit more. If I want to, I can bring that 4 off of the x, bring that out front, and now I have this expression. So, I think it's a subjective claim, but I think most people would agree that the derivative of this version is actually a little bit easier to do. So I'm going to differentiate this expanded log, quote-unquote, simplified version of g of x. So first I'm going to take a derivative of 4 times natural log of x, and that just becomes 4 times 1 over x. And now it's minus the derivative of this stuff. I'm going to have 1 over 3x squared minus 1 times the derivative of 3x squared minus 1. I have a little chain rule going on there. And so this simplifies into 4 over x minus, that'll be a 6x divided by 3x squared minus 1. Okay, so it feels like this question's done, but technically this question was asking for the tangent line. So we have to plug in 1, that was the point we were looking at, and see what we get for our slope. So this is what we called our slope. So we'll have 4 divided by 1 minus 6 over 3 times 1 minus 2 is 2. Oh, yep, okay. So that's 4 minus 3 is 1. The slope of this tangent line was just 1, and so I will get that y minus y1, which was the natural log of 1/2, equals our slope, 1 times x minus 1. So if I sort of rearrange this, I'll get y equals 1 times x plus this funny number, the natural log of 1/2. Alright, that's not too bad. Alright, this video is running a little long, so I'll tell you what I'll do. We'll work out example 6, and we'll see if we want to keep going to the next material. I feel like it kind of makes sense to keep going, so we'll see how long that makes this video. But okay. Example 6 says, determine where this new function, f of x equals x times the natural log of x, is increasing or decreasing. Find relative extrema, tell me about concavity, and tell me about points of inflection. Well, of course, all of these are just geometric code words that are telling you, take a first derivative, set it equal to 0, tell me where it's undefined, and then take a second derivative and tell me where it's 0 and if it changes sign. So I will first note that the domain of f, just in case we need to be careful here, is all positive numbers, right? Because again, those are the only numbers we're allowed to take a natural log of. And now, a formula for f prime, well, that's x times the natural log of x, all prime. So the derivative of x is 1, and then plus x times the derivative of log x. Alright, so here comes my new rule. That's x times 1 over x. That cancels pretty nicely. I get natural log of x plus 1. So I have a formula for log x. I have a formula for f prime. It's natural log of x plus 1. And I want to determine when is f of x increasing or decreasing. So I first want to see, hey, when is f prime equal to 0? Is f prime undefined? And you'll notice that f prime is only undefined where f was. So we really only care what's happening in the domain of the original, so we're going to focus on where is f prime equal to 0. This would be where is the natural log of x plus 1 equal to 0. And so I get natural log of x equals negative 1. And whenever you get an equation like this, it's easy and natural to feel stuck, but that's when you remember what we reviewed, right, about converting this equation into an exponential equation. Let me rewrite this as saying the log base e of x equals negative 1. And we can say this equation is saying the same thing as e to the negative 1 equals x. So this will be e to the negative 1 equals x. And so, look, this let us solve for x. X has to equal 1 over e. So, if we make a little sign diagram for the first derivative, we have this interesting point 1 over e. We don't want to go past 0. And so this is a sign diagram for the first derivative, f prime. So we can just check. We know that f prime is 0 at this funny number, 1 over e. But is it positive or negative before that? Is it positive or negative after that? Right? So if you recall the graph for these logarithm functions, they have a vertical asymptote at 0. And this natural logarithm has a base e that's bigger than 1, so it's a vertical asymptote that's going down to negative infinity. So as you plug in numbers over here, you're going to get negative values. And we can plug in some numbers bigger than 1 over e. Like you could try f prime of 1. That would be the natural log of 1 plus 1. Natural log of 1 is 0, so that's positive. So what does this tell us? We have increasing on the interval, this funny interval from 0 to 1 over e. Oh, sorry, that was where it was decreasing. It's increasing where f prime is positive from 1 over e to forever. It's decreasing on the interval 0 to 1 over e. And so when x equals 0, when x equals 1 over e, f of x equals f of 1 over e. That equals 1 over e times the natural log of 1 over e. That'll equal negative 1 over e. And so we can say the point x equals 1 over e, comma, negative 1 over e is a minimum. This answers the first half of this question. About increasing, decreasing, and relative extremums. Alright, let's finish this question up by seeing how hard it is to think about concavity. So we have that f of x was x log x, and we computed a derivative f prime of x turned out to be natural log of x plus 1. And so now I want to compute a second derivative. This one won't be too hard, because if you think about it, we just have to differentiate two terms. The derivative of natural log x is 1 over x. The derivative of plus 1 is 0. And this second derivative is positive on the interval where we're defined 0 to infinity. So we're always concave up. There are no points of inflection. So that would sort of finish up this long example. Okay. So we've already made this video long, so here's what I'm going to do. There's not much left. Let me scroll ahead. Yeah. So let me stop. Let me just finish this, because finally we get, just like we did for our previous exponential section, we first told you how to differentiate a to the x, and now we want to differentiate. Then we told you, we first told you how to differentiate e to the x. Then we said, and here's the formula for any a to the x. Similarly here, we said, okay, here's the formula for differentiating log base e of x, natural log of x. Now how do you do log base a of x? And just like I said at the beginning summary, here is the formula. Right, the derivative of the log base a of x, I'm just going to write this again, is 1 over x times 1 over natural log of a. And then similarly, if we have a function involved, so this would be like the log base a of u of x, some function, then the derivative, we're just going to follow the rule in red, but we're going to use the chain rule. So that would be 1 over u of x times 1 over natural log of a times the derivative of u of x. Okay, so to finish up this video, let's just finish up example 7, and then we'll pick up with part 2. So in example 7, they want us to find the derivative of each function. So here, dy dx, well, this should be a straightforward application of the rule for taking a derivative of log base a of x. So here we have the base is 2, so we're going to get that this is 1 over x times 1 over the natural log of 2. Okay, so for part B, we have y is log base 3 of a function. And so y prime is going to be the derivative of all this stuff. So we're going to take a derivative of all this stuff. And we're going to practice this. The derivative of log base a, or log base 3 in this case, is 1 over all the stuff inside the logarithm times 1 over the natural log of 3, and then finally the chain rule part times the derivative of 4x cubed plus 2x. So we can simplify this, and I'll move that 1 over log 3 out front. Natural log 3 times, let me write this as 4x cubed plus 2x, and then the derivative of that 4x cubed plus 2x I'll write on top. That'll be a 12 x squared plus 2. Okay. I think our last example for this video is this funny looking one. It has log base 9 of x divided by some other function. So there's a couple different ways you can do this. You can do this with the quotient rule, or you can do it as a product rule. If you want to use product rule, you can write this as the function 1 over x squared times the log base 9 of x. And if you want, you can write that 1 over x squared as x to the negative 2 times the log base 9 of x. That's just a little bit of rewriting. I don't know that it makes it terribly simpler. But if you don't like the quotient rule, then you're probably happy with rewriting it that way. Okay, so now I'm going to take a derivative of that, and now I get to use the product rule. So I get the derivative of x to the negative 2 times log base 9 of x plus x to the negative 2 times the log base 9 of x, all differentiated. And maybe I can color code. Let's see, we'll underline this one in red. So that first term, I bring the negative 2 down, and I subtract 1 from the power. So that's just my power rule that we're probably all really familiar with now. And now for my second term, this is where I've got to practice the new rule. So I leave that x to the negative 2. Okay, so log base 9 of x, that should be 1 over x times 1 over natural log of 9. Okay, so I'm actually going to rewrite these terms a little bit. It's not that these are wrong the way it's written, it's just we can combine it a little more efficiently. So, for example, that x to the negative 3 on the first term, I can write that as an x to the positive 3, all in a denominator. And this term over here, maybe I'll write the 1 over natural log 9 out front. This term over here, that x to the negative 2, I can write as a denominator. And look, I've got 2 powers of x there. So I've really got, in that second term, what I've really got is 1 over natural log of 9 times 1 over, that's actually x cubed. So if you wanted, you could rearrange this a little bit more and write it as one common denominator, as negative 2 log base 9 of x plus 1 over natural log of 9 all over x cubed. I think at that point this is mostly a cosmetic choice. And since we're coming up on a full hour for this video, which means it's going to take forever to load and process, let me finish up this, and let's finish up with our last popper questions. So question 4 for our popper, the answer is B, and question 5 for this popper, the answer is C. Okay, so in the remaining part of the next video that's related to this, what we're going to do is still differentiate with logarithms, but what's different is we're going to be given functions that have no logarithms in them, and we're going to put them in there and then take a derivative. So that's coming up next. And then one thing I want to alert you to, right, the notes that I'm being asked to use, the sort of protocol here, we have not answered a really important question, just like we left one unanswered from last time. These notes were all about formulas, and so a question from last time was, why is the derivative of this cool function e to the x, e to the x? A very related question is, why is the derivative of a to the x natural log a to the x? We told you that was it, and we just practice using that over and over. Now we have this leftover question, which was not addressed at all in these notes. Why is the derivative of natural log of x 1 over x? Again, I want you to feel really familiar using this over and over and over, but we never told you why. We just said, hey, here's the answer. Similarly, why is the derivative of log base a of x 1 over natural log of a times 1 over x? So I'm leaving these as questions that my video, which is just over an hour at the moment, I'm leaving these as questions that I should answer, and I have not. And so I just want to acknowledge that these are outstanding questions. If I have time to make an additional video for those curious students, I will. But if I don't get that video up in time, please feel free to Google around, look around for cool other YouTube videos that explain this. All right. I will talk to you guys later.